quadratic functions. So label the vertex and list all the transformations for the quadratic function, then graph each. So the vertex, we all know the vertex form by heart. Y equals a x minus h squared plus k, where hk is our vertex. So look in here, x minus 4, 4 must be my h. And I'm not adding anything, so k must be my 0. So I'm going to put that right in the middle on my table. 4, 0. So it would be easiest for me if I had points on either side that were 1 away each time. So they're consecutive numbers. So 3, 2, 5, 6. So I know my function, or my table, my points, are symmetric about the vertex. So what I get for 5, my y value I get for 5 and my x is going to be the same as what I get for my y value if x were 3. Same goes for whatever I get for x being 6, that y value is going to be the same as if x were 2. So 5 minus 4 is 1. 1 squared is 1. So 3 would also be 1. 6 minus 4 is 2. 2 squared is 4. So for 2, it's also 4. So transformations from my parent function. The parent function is y equals x squared. X squared, that starts at 0, 0. I'm going to start graphing the parent function, and then we can look at how my function is transformed. So 0, 0, 1, 1, 2, 2, and 3, 9. 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So negative 1 squared is also 1, negative 2 squared is 4, and negative 3 squared is negative 9. So that's my parent function. So I'm going to plot the points for this function on top of the same graph. So I'm going to start with my vertex 4, 0. And then 5, 1, and 3, 1. And then 6, 4, and 2, 4. So I notice my y values are the same difference as my parent function. It goes up by 1, and then it goes up 3, and then it goes up 5. Just like my parent function. So there wasn't any vertical stretching or compressing or anything like that. The only thing that happened was that my function went to the right 4. And the vertex is at 4, 0. So the next one, I notice that on the inside it's x minus 5, so my h is 5. I'm subtracting 3 on the outside, so my vertex is 5, negative 3. So again, I'm going to go and take sequential numbers, consecutive numbers. 6 minus 5 is 1. 1 squared is 1. Minus 3 would be negative 2. 7 minus 5 is 2. 2 squared would be 4. 4 minus 3 is 1. So I notice that the difference here is 1, and the difference here is 3, just like this function. and there's no stretching, no compressing happening. So it looks like it's only going to be like a left-right, up-down transformation. And I can prove that by graphing it. So 5, -3. And then 6, -2, and 4, -2. And then 7, 1, and 3, 1. So the graph looks something like this. So I know it is definitely a left, right, up, down. The vertex of the parent function is 0, 0. So it went to the right 5, and it went down 3. Left. That's very easy to see from the vertex form. So the vertex form is very helpful for graphing. So the next one, I have a 2 thrown in. So maybe we're going to have some stretching, some compressing. X plus 3, that's going to be a -1. -4. So I'm going to pick 0 and 1, -2, and -3. So if I put 0 in there, 0 plus 1 is 1, 1 squared is 1, 2 times 1 is 2, minus 4 would be -2. So that means -2 is also -2. If I put a 1 in there, 1 plus 1 is 2, 2 squared is 4, 2 times 4 is 8, minus 4 is 4. So I notice I'm not just skipping by 1 and by 3 and by 5 this time. There's something else going on. Since my x is not, or the difference in my x is still 1, the difference in my y is what increased, it's going to be a vertical something. And we got to figure out, okay, our vertex was -1, -4. And then 0, -2, 2, -2, 1, 4, and 3, 4. -3, 4. So it looks like my graph got thinner because the difference in my y increased a lot. That's called a vertical stretch. I took my vertex and I took I grabbed both lines and just pulled them apart. So it's a vertical stretch. And that was easy to see from the table, but I wanted to check the graph just to see what it looked like. Vertical stretch. It also went left this time, and it went down. So it went left 1, I can see it from my vertex, and it went down 4. So my vertex form is very handy. I'll give you a general case. Y equals a times x minus h squared plus k. So we have this in the notes from the very second week of school or something. It's very, very early in the school year. If a is greater than 1, that's a vertical stretch. If a is in between 1 and 0, that's a vertical compression. And that's meant the graph look wider, because all my y values are closer together. Then If H is positive, it's going right. If H is negative, it's going left. If K is positive, it's going up. And if K is negative, it's going down. So you don't have that committed to memory. Keep writing it down. Do whatever you need to make sure that it gets in your brain. Because this is not going away. It's going to be the rest of the year and in all your other math classes. So the next example, I have a fraction thrown in there. So that's A is positive, but it's less than 1, so that's a vertical compression. So that means I got the top and I got the bottom and I squished them down. I made the difference in my y value smaller. But my vertex, h here is negative because it was x minus h. So I subtracted a negative, and so we just say that's addition. So h is negative, k is negative. So negative 3 plus 4, that's negative 1. I'm sorry, it's positive 1. Squared is 1. 1 divided by 2 is 1/2. And then minus 6. So it's negative 5.5. So this is also negative 5.5. This is not going to be fun to graph with all the halves. Negative 2. Negative 2 plus 4 is positive 2 squared is 4. 4 times 1/2 is 2. 2 minus 6 is negative 4. So negative 4, negative 6. Oh, I graphed. That's funny, those points are opposite. And then negative 2, negative 4. And so my graph does appear wider because I squished it down. And my vertex moved to the left and it went down. Left 4, down 6.